Alright, I thought Alright, I thought I'd go through the solutions on this Skill 14 and see if I can help anybody. It's posted, the answers are posted on that Kia website, but I thought I'd give a detailed explanation of how I got these. So we see in the first few problems that we're given a polar graph. You have the pole here that in Cartesian coordinates, you kind of think of it as your initial point, is your starting point. Rather than calling it the origin, they call it the pole in polar coordinates. And you need an axis. They refer to this as the polar axis, and they typically, when you're comparing a polar coordinate system to a rectangular coordinate system, you line up the polar axis with the positive x-axis. So that's pretty typical how it's drawn, although you could orient it any way you'd like. We see here that our concentric circles have been divided into 24 equal segments. If you're working with radians, then each angle measure is pi over 12. So you have 1 pi over 12, 2 pi over 12, 3 pi over 12, and so forth. 24 pi over 12 is 2 pi. If you were working in degrees, these would be 15 degrees, 15, 30, 45, and so forth, all the way up to 360. All right, so let's take a look. What I suggest that you do when you're graphing these, take a look at your graph, at your polar coordinates. Work with common denominators. So here, with 24 equal divisions, if you work with a denominator of 12, because 2 pi radians is one complete circle, so the negative pi over 6, if I convert that to a denominator of 12, negative 2 pi over 12, I know that if I just negative angle measures are clockwise, so if I just count to 2, 1, 2 going clockwise, I'm at the circle that has a radius of 3, so go down pi over 6 or go counterclockwise pi over 6 units, and a radius from the pole go out 3 units. So, and mark that as A from your assignment. Alright, so for the next one, 7 pi over 4, 21 pi over 12. So here's the ray that is 21 pi over 12. The opposite ray, 9 pi over 12. So when I was counting this, I just counted 9 and then added 12, and 9 and 12 is 21. A radius of 2, go out 2, and that should be B. Label that point B. For number 3, 3 pi over 2, you may not have to convert that to denominator 12 because that's on the y-axis going down, but just for consistency, if we go ahead and write that as 18 pi over 12, and you can see that 3 pi over 2 is down here, or the 18 pi over 12. The 0.5, we're just going to have to eyeball it. We're just going to have to estimate it because our concentric circles here have a scale, a spacing of 1. So we really want a circle of 0.5, so we just had to eyeball that one there. All right, 2 pi over 3 converted to the 3 converted to a denominator of 12. Count over 8. If I go to 8 divisions, the opposite ray, if I add 12 to that, is 20 over there. And I need that, and this is why that I suggest that you start with the angle measure versus with the radius, because when I get to my 2 pi over 3, when I get to this 8 pi over 12, when I count over 8 spaces, because that's negative, I can't go out along that ray. I have to go in the negative direction to the opposite ray. So I'm actually going down here to 20 pi over 12, and so if I go down, you should label that D, and I had to estimate what 1.5 was. All right. Here it's already has a denominator of 12, so I counted 5 and then added 12, 17, and I drew this on here. You may need a straight edge and stuff, or at least I do, because if I come through, when I go through that pole, sometimes I accidentally come out on a wrong ray, and these need to be opposite rays. It needs to be a straight line going through there. So 17 pi over 12. I counted here's 17 pi over 12, and that's our outer circle there, concentric circle of 5 units, so label that point E. Here in number F, I noticed that 9 pi over 4 was bigger than 2 pi, so I found a coterminal angle. So I took away one complete revolution, and in order to do that, I got a common denominator, did that subtraction, and then, of course, I'm writing this in denominators of 12. So I counted over 3 pi over 12. But again, since it's negative, I can't mark this radius. This would be 2, comma 9 pi over 4 right here. You can't mark your point there because of the negative r. When we determine that we're going to use that ray to go in a negative distance, you go opposite that, and that takes care of the negative sign there. So you should have point F, and that may take a little bit getting used to with the negative r's. That's why I say find the angle measure first, and then go outward on that ray that you found. That if you're, say, here in quadrant 1, if it's negative, then you have to go to the opposite ray. Alright, so again here 13 pi over 6 was bigger than 2 pi, so I found a coterminal angle, took away one complete revolution, got pi over 6, rewrote it in terms of pi over 12s, 2 pi over 12. But when I count out 2, I'm not going to go out 4 units because that's a negative 4. I'm going to go to the direction of the opposite ray. That's why I say it's nice when you draw that line through the pole that you come out the other side, that you make sure that that's a straight angle, that you don't, with all those lines right there, if you don't have a straight edge. And I've got plenty of rulers, small 6-inch rulers back in the counter in a drawer labeled rulers, and you're totally welcome to borrow those. Those are there for your use. Alright, so this in number 7, this is where I labeled G. 7 pi over 2 is bigger than 2 pi, so I found a coterminal angle between 0 and 2 pi, rewrote it with a denominator of 12, counted around to 6. Well, again, 7 pi over 2, you know that that's going to lie on the y-axis, but I wrote it in the denominator 12, 18. So there was 6, and 6 plus 12, 18. This time my radian measure was positive, and the 13 divided by 4 is a decimal number, 3.25. So I just had to eyeball it. I came here to 3 and just made it slightly past that. So you just have to do the best you can if it's a decimal approximation when you're plotting those points. Now here on number 9, they give us a point in polar coordinates, r theta, and remember, because of coterminal angles, and also because we can have a negative r values, there's infinitely many ways to describe that same point in a two-dimensional plane. So what I did here is, if I'm using a positive r, if I kept 4 as positive, I wanted to create a table, create a list of all the coterminal angles. Well, not all, but with 5 pi over 6. So I just went out 3 units from 0. When I compared my list and looked, I saw that 2 of them in my list were among the lists that we're supposed to recognize as the same point. So this 4 comma negative 7 pi over 6, if you were to plot that point, is the same point as 4 comma 5 pi over 6, because negative 7 pi over 6 and 5 pi over 6 are coterminal angles. All of these points in this table are plotting in the same spot on a two-dimensional plane. It's the same point, just different ways to represent that point because of the coterminal angles. So again, among this list, we see negative 7 pi over 6 and 29 pi over 6 among our choices. But however, what if we wanted to list the possibilities with a negative 4? So there, you take this angle. Remember, you want to be on the opposite ray. In the opposite ray, all you have to do is add pi or add 180, so or subtract. 5 pi over 6 plus pi got me to 11 pi over 6. So I know that negative 4 comma 11 pi over 6 is the same point as 4 comma 5 pi over 6. Go around almost one complete revolution, and rather than going out on that ray of 11 pi over 6 because it's negative, you have to go in the opposite ray, which hey is 5 pi over 6, and you go out 4 units. So they're the same. So then I took 11 pi over 6, found its coterminal angles. Whenever I'm finding coterminal angles, I try once again to work with common denominators. When you're comparing fractions or you're adding and subtracting, it's clearly easiest if when you make these, it's necessary to make a common denominator. So I can see here that these are, I'm just taking that numerator and adding 12 each time. Negative 25 plus 12 got me negative 13, plus 12 got me negative 1, plus 12, 11, plus 12, plus 12, plus, these are 12 pi over 6 units apart. So when I did the same thing with number 10, but when they gave me the radius, the original one is negative 3, when I looked at coterminal angles to 5 pi over 3, I added, multiples of complete revolutions, multiples of 2 pi, rewrote 2 pi with the denominator 3, constructed my table, looked among this, and I don't see any of these as possible answers among that choice in number 10. When I converted it to a positive 3, I couldn't use the ray 5 pi over 3. I had to use the opposite ray. Here I subtracted pi. I could have easily have added pi. When I subtracted pi, 3 comma 2 pi over 3 is the same point as negative 3 comma 5 pi over 3. So now that I have my angle measure, I'm going to find coterminal angles by adding or subtracting complete revolutions. I constructed a table. Amongst these tables here, I see that this 3 comma 2 pi over 3, 3 comma 8 pi over 3 were in our list. So those were the only two that I see among that list that all, that plot to the same point as negative 3 comma 5 pi. It describes the same location in a two-dimensional space. All right, so here we have several that they give us our polar coordinate, and they want us to convert it to rectangular coordinates. So hopefully this is a little bit familiar, because this is what you were doing with vectors when we broke it up into horizontal and vertical components. So this pole here, this radius out from the pole, theta is measured positive counterclockwise from the x-axis. So you can construct a right triangle here, and through SOHCAHTOA you can easily illustrate that this leg is the hypotenuse times the cosine of theta, that this opposite leg is the hypotenuse times the sine of theta. So using these two equations, it's just a matter of substitution. Replace for the x, it's cosine. Replace the r with 4, cosine of pi over 4. I don't have to use a calculator for that. That's on our unit circle, and I, through experience, recognize that as being radical 2 over 2. Simplify that. I have an x coordinate, 2 radical 2. Y coordinate is the same. With an angle of pi over 4, we see that that's an isosceles right triangle, and it makes sense that x and y are going to have the same coordinates. All right, number 12, this is done in the same way. We're given a radius, we're given a theta. I came over here and used these. These are just the formulas that were cut and pasted right out of your notes. And then Skill Packet 14 through substitution, negative 3/2 times cosine of 4 pi over 3. 4 pi over 3 is a point on the unit circle in quadrant 3. X and y are both negative in quadrant 3. So this cosine of 4 pi over 3 is negative. Sine 4 pi over 3 is also negative. Cosine is the x coordinate on the unit circle. Sine is the y coordinate. So I didn't need a scientific calculator, although I suppose that's okay, that many people may just key this in. Just make sure that you're in radians. But this is one that like I say, with one of the special right triangles, either 30, 60, 90, or 45, 45, 90. That's how we constructed the original unit circle, and then we of course used our addition and subtraction formulas to get expressions for multiples of 15 degrees or multiples of pi over 12. But anyway, using the unit circle, I get negative 1/2 for cosine of 4 pi over 3, negative radical 3 over 2 for sine 4 pi over 3. So here's my final answer. This polar point in rectangular would be plotted as 3/4 comma 3 radical 3 over 4. Now, in rectangular coordinate systems, every xy is unique. In polar, we can add or subtract complete revolutions that 4 pi over 3, or we could make this negative radius a positive radius if we change this angle to go to the opposite ray by adding or subtracting pi, and then from there finding a list of coterminal angles, just like that previous problem. So while there's infinitely many ways to describe a point in polar coordinates, there's a unique way to describe each point in rectangular coordinates, and that's important to understand that distinction. Here in number 13, it's again very similar to the previous problems. They give us a radius, they give us an angle measure. We use these formulas: x equals r cosine theta, y equals r sine theta, through substitution. 3 pi over 2 is a point on the unit circle down there that has coordinates of 0, -1. It's on the y-axis. So if you're on the y-axis, the x is 0, so that's how we're getting cosine of 3 pi over 2 being 0. And because you're below the x-axis, the y-coordinate there is -1. So this 5 comma 3 pi over 2, if you plotted that point in two-dimensional space, and then you plotted this in rectangular, if you lined up the polar axis with the positive x-axis, those points would be, it's the same point in two-dimensional space. Alright, so we're given again polar coordinates. We're asked to convert it to rectangular coordinates. So we use the formula that x is equal to r cosine theta, y is equal to r sine theta through substitution. Pi over 6 is again a point on our unit circle, the x-coordinate radical 3 over 2 and the y-coordinate 1/2, or at least I hope that's true, otherwise this problem I've done it wrong. Yeah, that is the same. Alright, so that's what I get for number 14. Again, these are now being repetitive, or at least I hope that you find that they're being a little bit repetitive, because we're identifying what's given, r and theta. We're just through substitution. The x-coordinate is r times cosine theta. The y-coordinate is r times sine theta. If they give me a point that's on the unit circle, I don't need a scientific calculator. If they give me a point that is not, a known coordinate on the unit circle, then I can use my scientific calculator and estimate the angle measure, estimate the ratio, the proportion, the ratio of the angle. So this is what I get for number 15. In 16, again, it's asking us to convert from polar to rectangular, use those coordinates, use substitution. Now here I did notice that 19 over 6, that 12 over 6 is 2, so I knew that this went around more than one complete revolution. So to use my unit circle, I'm not going to see an angle measure of 19 pi over 6, so I subtracted 12. 19 minus 12 is 7. I subtracted 12 because 12 over 6 is 2, and I subtracted one complete revolution. I subtracted 2 pi. So 19 pi over 6 minus 2 pi is 7 pi over 6. 7 pi over 6 is an angle that I see on my unit circles, and so the x-coordinate was negative radical 3 over 2. Oh, did I do the y? Oh, maybe I did on the next slide. Yeah. Again, 19 pi over 6 is coterminal to 7 pi over 6. So those coterminal angles have the same trig ratios, and I get 15 over 4. And of course, if you have decimal approximations to that, that's fine. But again, when I'm using when they give me values of the unit circle, I don't have to approximate. I can calculate exact values. All right, so now let's see, before they were giving us the polar coordinates. Now they're giving us rectangular coordinates, and they're asking us to come up with the polar coordinates. So the first thing that I do is visualize the point 4, 8. If you're graphing that point, 4, 8 is in the first quadrant. Move to the right 4 units, then up 8 units, and you're in quadrant 1. So I know that in quadrant 1, all of my trig ratios are positive. I like to work with the reference angles. So if you're in quadrant 1, this angle theta that we're trying to get for our polar coordinate system is the same as the reference angle in this case. So we refer to the same picture that we had before here, where we had that right triangle, only this time we're given x and y and trying to find r. Well, from the Pythagorean theorem, we know that if you square the sum of squares of the legs is equal to the hypotenuse squared. And don't forget that if you're trying to find the radius, you have to take the square root of that. Now, we could take the positive or the negative square root and work accordingly, but I typically will use the positive square root when I'm doing my angle theta, because this triangle could be oriented in quadrants 2, 3, or 4. I use this as my reference angle, and then using my reference angle, I find the angle that I want, that theta. And like I say, if you're in quadrant 1, this theta is also the reference angle, so I didn't have to do any kind of adding or subtracting 180 or subtracting this angle from 360. I had my calculator set on radians, that's why I wrote rad there. So anyway, this is my answer for number 17. Let's take a look at number 18. Negative 4, 2. If you go to the left and then up, you'll be in quadrant 2. So again, when I substitute in x and y into my formula to calculate r, when you square it, if you're using a calculator, make sure you put parentheses around it so you don't have a sign error. But with 16 plus 4, that's square root of 20. 4 is the perfect largest square that divides 20, so I simplified radical 20 to 2 radical 5. So there's my radius. Since I'm in quadrant 2, I first found the reference angle. So when I'm finding the reference angle, when I'm doing my y divided by x, I ignore the sign SIG, and I just use this as positive 4. So this angle, this point 4636 radians is my reference angle. If I'm in quadrant 2, let's maybe sketch that out for you real quick. If I'm in quadrant 2, this is my reference angle. So that's the angle I just found. Now, what I want is this angle, this theta, okay? Because from the positive x-axis to this terminal ray that's here in quadrant 2, well, I'm going to take pi, which is together, these two are supplementary. Together, this and my answer have to add up to pi, so I took pi minus my reference angle to get my final answer of theta. So remember, if you're in quadrant 2, then to find the angle, it's pi minus that reference angle, and it was in quadrant 2. Now, had I been in quadrant 3, it would have been addition. Had I been in quadrant 4, it would have been 2 pi minus that. So it was crucial for me to identify that I was in quadrant 2 if I'm going to work with these reference angles. So anyway, for number 18, that's my final answer. Let's take a look at these others and see if they're good. This one is in quadrant 4. If you go to the right 6 units, then go down, you'll be in quadrant 4. I don't suspect you'll have any trouble calculating the r. It's just straight out the square root of x squared plus y squared. Make sure that you don't make any silly sign errors. Remember that this first term is positive. The second term will always be positive because you're squaring it. You're adding them together. When I did that, I got 144, and the square root of 144 is 12. Now, here I am in quadrant 4, but I'm going to work with the reference angle first. I'm just going to ignore this negative sign. 6 radical 3 divided by 6, the 6 is canceled. The inverse tangent of radical 3. Hey, that's I can use my unit circle. I didn't even have to use the calculator, and I have 60 degrees, or pi over 3. So, but remember, I want to be in quadrant 4. I want this theta to be in quadrant 4, so it's 2 pi minus that reference angle if you're in quadrant 4. 2 pi minus pi over 3 is 5 pi over 3, and that's my answer. Now, if you're checking your key, checking your answers against the key that's against the answers that are on Kia, you're going to see that it doesn't say 12 comma 5 pi over 3, that it says 12 comma negative pi over 3. It's the same. There's infinitely many correct answers. There's infinitely many different ways to describe this r theta. 12 comma 5 pi over 3 is the same point as 12 comma negative pi over 3, because these are coterminal angles. If you just subtract a complete revolution, the 5 pi over 3 minus 2 pi is negative pi over 3. So while these two look like they're different, they're actually the same location in two-dimensional space. It's the same point, just different ways to describe the exact same point. All right, so here again in number 20, we're given rectangular coordinates. We want to convert it to polar. 5 comma 1 is in the first quadrant. I know that the reference angle is going to actually be theta, that it's its own reference angle. It's going to be my answer. The square root of 5 squared plus 1 squared, radical 26, and I couldn't simplify that. I did have to go to the scientific calculator, make sure that I was in radians here, did inverse tangent of 1 over 5, got 0.1974 to 4 decimals. Since I'm in quadrant 1, hey, that is the answer. I didn't have to subtract pi or add pi to it. I didn't have to take 2 pi minus this answer. I just said, hey, I'm in quadrant 1, boom, that's my answer. All right, so here I'm in quadrant 3, so I know my reference angle is always a positive between 0 and pi over 2, or between 0 and 90. So if I'm in quadrant 3, when I find that reference angle, I'm going to have to add pi radians, or 180 degrees, to it to get the theta that I want. Having a negative x and a negative y, quadrant 3, make sure if you are using a calculator that you have parentheses around the negative signs. You don't want to make a silly calculation error here. 4 was the largest perfect square. I think that was 104 when I calculated that. 4 divided that, so then the square root of 4 is 2. So I've got 2 radical 26. My reference angle, when I take the y divided by x, I ignore the sign. I just take the positive values. Got that, and it's always going to be an acute angle as my reference angle, but since I was in quadrant 3, the angle of interest is pi plus that. So boom, there I've highlighted my answer, and that's hopefully what you're getting as well. In quadrant 2, identify x, and how did I know I'm in quadrant 2? Because the x is negative, the y is positive. If you start at the origin and go to the left and then up, you're going to be in quadrant 2. So it's just simple substitution to calculate the radius. Don't forget to take the square root. Be careful with sign errors. If it says it wants an exact value, you'll have to write your answer in radical form. If it says, to approximate it to a certain number of decimals, then hey, there's no problem taking the square root of that and using it on your calculator and using a decimal number. Like I say, here I'm finding the reference angle. I ignore that negative 7, just do y divided by x. This 4 over 7 is not a ratio that I'm going to see on my unit circle, so I had to use a scientific calculator. When I did this, was in radians, and I kind of like to write that in my own notes. Just to, you know that the radians is implied because there was no degree symbol above there, right? So without that degree symbol, the radians are a dimensionless quantity, and so you will see that they often don't write radians because, like I say, it doesn't have any dimensions to it. All right, anyway, since I was in quadrant 2, it's pi minus that reference angle, or 180 degrees minus that reference angle. So my final answer is here. I've carried that out to 4 decimals there, but I think, however, on the answer key on Kia, it's just to 3 decimals. All right, hey, that was it. Hope that helped, and talk to you later. Bye.